Hello, everybody. Welcome. Because of this coronavirus and school closure and everything, I really wanted to look at some very important part of math competition solving, problem solving in general. And one of those very important topics is combinatorics and probability, right? Because that is extremely important when you have casework counting, all of those things, even algebraic equations, you can use combinations and counting. So let's discuss some of the main combinatorical identities and how to prove them. We're not going to be using induction or algebra or block walking. We're going to be using committee forging arguments because what it does is it improves your combinatorical logic in general, which is extremely important because we're based on counting and probability and combinatorics. So the first one is easily the most simplest one. It's n choose k, sorry, plus n plus 1. No, n choose k plus 1 equals n plus 1 choose k plus 1. This is Pascal's identity. It was found by Pascal, but as we know, many of us know, we don't know exactly who found it. It was used years ago, not billions, but it was used years ago. All right. Ooh. Yeah. So I already wrote Dan. You can probably see what this is leading up to. The proof. Let's give away a little hint. Let's look at the right hand side. What the right hand side is stating is that we have n plus 1 people and we're choosing k plus 1 of them to be on our committee. Right? So let's assume one of them, like we remember, is Dan. Okay? Dan is one of the n plus 1 people. Okay? Now, let's look at the two left-hand side equations. We'll start on level equation 1 and equation 2. They're not equations, so let's actually call them combination 1 and combination 2. Combination 1 is stating that we have n people and we're choosing k. Right? And then the other one is n people and we have k plus 1. So let's look at Dan. Right? He has two options. He can either be on the committee, right? On the k plus 1 committee. He could not be on the committee, right? Dan has two options. Let's look at what Dan does if he's not on the committee. If Dan is not on the committee, we already know that we have n people left because n plus 1 minus 1. But we still have to choose k plus 1 people. So when Dan is not, right? And when Dan is on, right, we still have n people because n plus 1 minus 1, but we already chose one of the k plus 1 people. So now we only have n choose k people, right, when he is on. And as you can see, equation 1 and equation 2, or combination 1 and combination 2, are the same. So this is a really good way of looking at Pascal's identity, and it's also helpful for tackling identities that you don't know. Try to think about one person in general. Alright? Okay. So that was Pascal's identity. Next identity we'll be looking at is a much more complex one. It is the hockey stick identity. And it is called a hockey stick identity because it looks like a hockey stick identity when shown on Pascal's triangle. Right? So basically it's n, choose n plus 1, choose n, plus dot 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 plus n plus k choose n. This is just equal to a much more simpler equation, which is why this is a amazing problem solving tool. N plus k plus 1, choose n plus 1, people. This is super helpful because it helps us solve problems like giving money away and the famous one, a plus b plus c is equal to d, find the number of ordered triples. Right? It can be used for those type of problems. So this can be used for algebra also, which is pretty very important because algebra is one of the main parts of the AMCs and the AMEs. So let's try to prove this. Again, look at the simpler combination. In this case, it's the right hand side. N plus k plus 1, choose n plus 1. Here, let's try to have just one person, right? Or Dan. Can we do something with Dan? Clearly, we see that this is one person less, so we might have something to do with Dan. But we have a lot of different formulas, or not formulas, different combinations. And Dan, let's just start with Dan, okay? Let's say we have a bunch of people. We'll call it Dan and then some random person, right? So it's an easier way to group this would be using letters. That way we could clearly emphasize the order. So we need to use order here, right? So we have x of 1, x of 2. Let's just go at number 3, 4, 5, all the way to let's say the first person, and we have all the way until we need n plus k plus 1 or k plus 1. Well, let's just go to k plus 1. We have n plus k plus 1 people because we're choosing what's n plus k plus 1 people, right? So let's just say here for the n plus k, let's start here. Let's say we're choosing all the numbers because let's assume that these are numbers. It can be any objects, but let's say the first term is going to be x of 1, which we're going to, like I said, I'm just going to make things simpler on us in our notation. We're going to call that 1. Right? So now we only have n plus k objects because we already chose one, and we have to choose n of them. So that's what this equation is. Okay? The second equation should be n plus k minus 1, choose n. Right. We already did all of the equations that start with 1. So let me just show you a basic example. Let's say we have 1, 2, 3, and 4. Alright? And we're trying to find the number of ways we can, via 5 and 6, and then we choose 3 of them. Once we finish, let's say we already choose 1, so now we're just choosing 5, choose 3, right? Now we already have done all of the options for number 1, so we can't choose that again. So now what is done, and then we start with 2 as our next number, 4 choose 3, then 2 is done, and so on. Let's try to use that argument here, because that's basically what we're going to be doing with all of these proofs. Right? So we already chose number 1, so let's choose number 2. It's already one of them. This means that we only have n plus k minus 1, because 2 of them are already chosen, so n plus k plus 1 minus 2 is n plus k minus 1. And we're choosing n of them, because we already have 1 chosen, that's our 2. If we keep on committing to this argument, we end up at n choose n. That is where we have k plus 1 people, and then we only have n people left, so this ends up being 1. We have k plus 1, and then a bunch of numbers all the way till n plus k plus 1, so there's only n plus 1 people remaining. And if you notice, this having k plus 1 as the first one is the last possible committee. Having k plus 1 as the first term, there's no other committees that we can form unless we change the size, or really lower the size. So we have been through every single committee, and this is why this proof actually works using combinatorical logic. The last one is called Vardadon's proof, or not proof, identity. This is more of when you have different types of objects. Right now we haven't been really looking at the type. We just call them like x01, x02. But here we're going to be looking at, we have a group of objects. So we're going to be looking at more groups. Right? Let's just look at the identity first. We have m plus k choose r. This is gonna, I hope you know your sigma notation. Is equal to the sigma notation k equals 0 all the way up till r m. Ooh. Yikes. Okay, I'm gonna make this n. That way I don't, my variables don't conflict. And then m, we have r minus k. So this identity, I don't know how you actually say Verdon or Vardonde, but this identity is when you have different groups of objects. So let's take a look at this. Right? We have m plus n objects, and we're choosing r. And then we look at the right hand side, and we have m and n as two different combinatorics. So what we're gonna do is assign group, or not group, let's call type 1 to m, and then type 2 to n, right? So what we're doing here is that we just have type 1 plus type 2 group of people, and we're choosing r of them. So let's, instead of actually like trying to look at the left hand side, let's try to see how we could actually actively solve this. So, right, the first thing we could do is we could have choose 0 of group 1, and then we would have r minus 0, so r, and choose n of them. That's the first case. Second case is we have m, and we choose one of them, and then we have r, and we choose r, not r, n, and we choose r minus one of them. Right? We could keep building this argument. I'm kind of proving it through algebra, but it works. It's not exactly algebra, but I'm not using actual logic. I'm actually mapping out the problem. We get to r on the m side. M times 0 and n. What we have done is we have listed every single possible option. And then this is where we get our sigma notation from. We can also test if my sigma notation is correct. We start at 0, and then we go all the way up to r. And as you can clearly see, my sigma notation is correct. And this is another important identity when we're solving with different types of problems, types of objects, as I told you. And this is a good way to do it. We're just looking at case by case. We didn't do that we kind of did it on the other ones, but we basically looked at just the overall argument. And here we're looking at every single case and solving. This is an easier formula. This is an easier identity to prove, but You don't even need to memorize this final bit. You don't need to memorize this. So what I'm gonna just do is cross that out. You don't need to memorize that. Just knowing this will help, because the thing about this is that you could easily list out every single case. It would not take that long. Just knowing this. And if you do have this, right, you could know when you have this thing here. Okay, I'm gonna undo that. It's useful to be able to look at this. But some certain times when you do actually need to make this into a simpler case, like this, case by case by case, you don't need to memorize. You shouldn't really memorize this. And the reason is just use your logic and think it out. This is more of a logic think out problem. Alright, this is the end of today, and next class we're going to be reviewing partitions. And not only are we going to do partitions, but we're going to also see, what I'm going to do is use block walking. I want to show you Pascal's identity. We're going to do partitions also. So stick around and remember the combinatoric identities. If you want me to review it, if you want me to prove it using other 4 ways, just put it in the comments below, and I will like that. Or not like it, I'll make a video on it. Alright? Bye.